just showing up here and doing the big thing as well. How's it going? All right, let's first, before we even start, we're going to talk about C-strings. There's a lot of cool things about C-strings. The only thing you need to know about C-strings, though, is actually contained in the world's largest ball of twine, the motto of the world's largest ball of twine, started by Frank Cooper in 1953. Cocker City, Kansas. Woohoo! Thrift, patience equals success. There you go. Now you know everything you know about C-strings. Thrift, we'll see thrift, how we're keeping the number a bit small. Patience, because we're going to get some seg faults and some sadness, but then we're going to triumph. That's our plan. All right, let's do a check-in. This is a good point just to kind of touch base on things that happened this week. Everybody got to go to lab this week. Lab love? Lab love. Lab leader love? Let's start with, oh, well, not quite that love. Lab leader appreciation. Let's go with that, right? Lab is super important, so I hope that you're kind of getting the emphasis that in lecture, Chris and I can get up here, we can draw pictures and wave our hands and talk about stuff, but it's not really going to be real until you get your hands on the compiler and the debugger and those bits and the programs and sort of see that system and kind of make things happen and really get there. And so the lab is super important for that, right? There's this time to dig in, get stuff done, to have your lab leader kind of circulating and keeping you moving and doing that stuff. So hopefully you are finding that to be a very valuable use of your time and you are glad that you are doing that. It also is really critical for setting you up for the assignment, right? So a lot of the things you did in lab are actually just repeated in the assignment in slightly different forms, right? So that the idea that we're kind of staging it to where you see it in lecture, you get to manipulate it in lab, and then you go off and do these cool things on the assignment. So hopefully that's kind of working. So feeling good about lab, liking lab is a good place to be. The forum is happening, right? So if you have not been on the forum, I encourage you to go check it out and see. I really appreciate all of the very generous spirit in which answers are being given by everyone and exchange and discussion and sort of talking about things. So a great place to go look. Even if you don't have questions of your own, you're too shy to get them out there, there's a good chance somebody else has the same question and already asked it for you, and so you can just kind of follow along and get the benefit of that answer just by being there. And so please do keep an eye on that. Assignment 0, we graded assignment 0. Mostly we just gave you all 20 points. It was free, right? We have 5 points to spare. But that was great. We're glad to see you guys, got up and running, got a compiled, got a program going, and stuff like that, right? There will be sort of more extensive review and whatnot on your code that we're going to do once you start writing real programs. But in this case, we did take a little look at what you were doing there and kind of try to get you on the right track, make sure that you have your basics down and are going forward on that. All right, one other thing. Who is Ambosca? Is he really a bad guy? Does anyone know who Ambosca is? He's the bad guy, right? He's the bad. Okay, I have to tell my husband's going to make me tell you this because I mistakenly let him know the secret. Ambosca is actually my husband. And we use his account because we needed an unprivileged account that we kind of set aside. We kind of just started doing so he was a Stanford alum, so I got to use his account. But he's the scapegoat for everything. It turns out, little does he know. And so when I told him that, he made me insist that I come and tell you that actually he's a good guy. He would never break into your system or steal your Equifax credit data or any of those things. So he did not do those things, and he is legit. All right. Anything you guys want to tell me about how things are going this week? Nothing to say?
The bees are dying.
The beans are dying?
The bees.
The bees?
Like honeybees.
The honeybees? Okay. I cannot answer. There's nothing more I can say after that. I'm going to run the blue light. Run the light. Everybody run the blue light now? Out to Baylands. Running by the blue light. All right, well. Okay. All right, that's all we got here. All right, what are we actually going to do today? Well, we're going to talk about C-strings, all about C-strings. I'm going to start with just the characters, right? Single characters, right? Just being, one of the integer family types that Chris has been giving you all the ropes on, right? So just kind of review how that plays out in terms of interpreting those integers as character data. Then we're going to start stringing them together into sequences, make ourselves some strings. Now, a lot of what I'm going to try to do today is I'm going to try to play this sort of game where we pretend that we don't really know anything about strings, where we say, well, clearly, in a language, where we're trying to program and deal things, we need to have these sequences of characters and make sense of them and be able to treat them as a string. We're going to discover that C's ability to provide that as a kind of a clean abstraction is really limited. C is so close to the metal and so exposing kind of what the underlying system is that what it's giving us is a pretty raw interpretation of a facility that will let us kind of treat a block of memory as a sequence of characters is about all we're going to get out of it. And as a result, it's going to have pretty little facilities for this, right? Not a lot of fancy stuff, and a certain amount of dangerousness in the way that it's going to present it to us in terms of our use as a client. We can definitely kind of make some pretty bad mistakes in there. So we're going to try to kind of stick on it for a little bit just to see its abstraction. Then what we'll kind of get to, and hopefully some of that today, and if not, what we don't do today, we'll be picking up on Monday, right? Which is then really trying to understand, well, how do we really get down and dirty with the strings? And if we need to know how its implementation works to be able to use it correctly, then what are we going to have to kind of inform ourselves about that and how to be successful with that? I put a big note of like asking questions, right? The next couple lectures I'm going to be doing is I'm going into all the kind of gory details of pointers in C. Pointers are incredibly essential to understanding C and the memory model of the address space, and the whole system, right, kind of hinges on really getting this concept really solid. So I'm going to spend some pretty this lecture and all of next lecture and some of the following lectures, right, just going over pointers in different ways and things about them. So it's going to be a lot of topics, like a lot of time on this. It is a great time to ask questions. Because you don't want to kind of leave yourself with sort of misconception and building on that. This foundation is super, super important that we need to have in this grade going forward. So do make your needs known if something's kind of going too fast or not quite jiving with your understanding. My vision is a little bit weak, right? So I'm not actually that good at seeing when your hand is up unless you kind of do something a little bit more animated. So don't be shy about trying to draw attention if you know you need to get my attention, and I'm not actually ignoring you, I just can't see that well. Okay. All right. So let's just start with characters, and kind of this is coming from what Chris said, but then I'm going to actually kind of drill down to specifically the use of a one byte, twos complement or unsigned bit pattern as a character, right, is kind of fundamental to the notion of C. So the car type, sometimes people call it char, some people call it chair, some character. You think you call it care. No one ever calls it care, though. I would say car star. All the work, right? You won't be kicked out of the club for saying it wrong. But char is the kind of fundamental atomic type of the C language and of the machine in general, right? We've seen that there are bits that are underneath it, but those are kind of like those subatomic particles that we can only get to with the sort of high-powered laser gun here, right? We have to dig it out with these masks. So the unit of memory that's interesting to us is the byte. We talk about memory sometimes as being byte addressable. So if we were to line up, if we have some number of 2 gigabytes of memory available to us, right, we can line it up and count them from 0, 1, 2, 3, all the way up to 2 billion. Each of those bytes has an address. It's like a whole row of post office boxes, right, over there at the Stanford quad there, quad where it's White Cloud. And you just go open up that box and there's a byte's worth of stuff in there, right? That's what we've got in memory. It calls it a car, right? It is by definition, right, in the C language it says size of car is 1. There's no such thing as any other size of car, right, that exists out there. And so in code, for example, you'll see size of it, size of on. Sometimes trying to decide what the native type for those things is on the platform. You should never see an expression size of car. By never, I mean, anytime you do see that, that's a sign that somebody didn't actually understand kind of what the ground rules were here, but it's actually just uniformly 1. That's like multiplying by 1. So if you were to see a bunch of things that say, take the number of bytes I need to multiply by 1, that's what I see whenever I see, n times size of car, I think, okay, n times 1. Let's just get rid of the 1. How about n? They may be signed or unsigned. It turns out it's not that important to know whether the default is, whereas for int, long, and the other integer family types, they default to signed unless you say otherwise. For car, it does not default to either. The standard says it's implementation defined. That means the compiler of the system gets to decide what it is. So some systems they will be signed, some systems they'll be unsigned. If you really care, you can always add the signed or unsigned yourself to be definitive about what you wanted. Mostly does not matter, but just sort of in your mind, it has a little effect on when we were shifting it or we were promoting it, right? What's going to happen in terms of the upper bits? The standing asterisk step. So we've got this 256 patterns, 8 bits, 2 to the 8, 256, right? They're just numbers, right? When we think of them as binary polynomials. Okay, here's the number 7, 0, 0, 0, 0, 0, 0, 1, 1, 1. Okay, we've got that. What character is that? Is that the digit 7? Is that the letter G? Is G the 7th letter of the alphabet? Maybe? I don't know, somewhere. What is it? It's arbitrary. Utterly arbitrary, right? When we map them from binary patterns to numbers, right, we have kind of a meaningful way to say that's 1, that's 2, that's 4, that's 10. But taking the 10 and saying 10 is capital A, that's just completely arbitrary, right? Someone needed to sit down and make it up and come up with a mapping. It turns out, though, that arbitrary is maybe probably the one word for it. It's a matter of making a choice, but there are better and worse decisions in there. For example, you could just go through and randomly assign the characters. Here's A, and next to it is the pound sign, also known as the hashtag. And Beethoven will never live down having things being called by my kids in C hashtag major. Okay, no, it's a sharp sign. But you could put them there, A hashtag, and then number 6 and number 42. Like you could just spread them all over the character set. It doesn't really matter, but you're definitely not leveraging the power of the fact that if we sequence them in such a way that, for example, we go from A to Z, right, we're going to have this neat underlying arithmetic property that if we start with the character A, and since characters are integer family types, we can do integer operations on them. I can say char plus plus, like CH plus plus, and that advances by 1. So it moved to the next slot in the table. Well, if I put A next to B next to C, right, then I can actually walk through the alphabet by starting at A, which is hex 41, and saying, oh, plus 1, plus 1, plus 1, and I work my way through the alphabet. So, in fact, the digits are in order, the uppercase alphabet's in order, the lowercase alphabet's in order, and then the other ones are kind of just jammed in the little spaces around there, right? The other critical thing about making that assignment is making good choices. There's also huge value in standardization. If I type up a document on my computer, and my computer uses 41, hex 41 for A, and your computer chose to use hex 72 for A, then when I send my document to you, it's really just zeros and ones. It doesn't have an A in it, right? There's not an A in my document. There's the number 41 in binary, which when it's transmitted to your computer, if it does not turn back into the capital A, right, then we will have been unable to communicate there. So being able to exchange files, send emails, go to web pages, and see the same letters for each of those same numbers is actually really critical to the interoperability of the world. So ASCII was actually a committee formed. It's the American Standard Code for Information Interchange, right? That was the kind of motivation. We got to be able to talk, and we all need to just get together. It does not really matter what we put where. It does matter that we agree. The ASCII is a huge success story. Our industry, on a whole, has a very spotty record with standardization. Just ask yourself how many different dongles you have to talk to your different generations of Apple products, right? Or how many peripherals, right, used to work on your machine and don't anymore as you upgrade and things like that. Like there's just kind of a lot of, constantly move the technology forward, get the next best thing, the better thing, and leave this behind. ASCII, in this case, right, is a great standard because, in fact, everybody needs to do this with basic data. As soon as we start talking about, though, anything fancier, we need E with an accent on it. We need the upside down exclamation point. Things really break down very, very quickly. So the ASCII only handles the 0 to 127 case. It leaves the upper bit clean. So the MSB, the most significant bit of an ASCII character, has a 0 in the most significant bit. Sometimes that bit was used actually as a little bit of a check on the integrity of the data. So if you had a data stream that was coming, it might still come in 8-bit chunks, but then the MSB would be set or not set depending on whether there was an even or an odd number of ones in the other 7 bits. And if it ever was out of sync with it, then it would give you some clue that the data had become corrupted. So sometimes that gets used. Nowadays, it turns out there's also a mapping of, well, once you get to those characters, 128, 129, and above, right, 200, what are they? All right, well, it turns out this is a place where the standards completely broke down. So here, let's show you this. This is actually kind of a little bit entertaining to observe. So here I'm going to show you that I'm the laziest person in the world, and there are many things that I will do that I will promote to you in the name of pro tip and efficiency, but you can actually really just translate in your mind to think, that is the laziest person I've ever seen. I just typed myth, and all of a sudden, I'm on myth. And there were 2 things that made that work, right? I have an alias. Aliases are good, so that was talked about in the forum, actually just a day ago. So making up shorthand names for commands you type a lot. And then I also have set up the passwordless authentication through something called GSS API. So if you're curious, write that down, Google it up, and learn what you need to do to get yourself this backstage pass to myth on a moment's notice. So for example, if the people were beating down the door and I had to get to myth and run sanity check to fight off the intruders, I'm going to be there way faster than all of you. All right, so there I am on myth, and I'm going to make this bigger because everybody likes big. Big is good. And so you say man ASCII, woo, and you have to be able to type. That's also why I'm lazy. I'm a bad typist. And so it tells you, oh, okay, yeah, what happened in the picking up these? Oh, look at all these crazy things. Yeah, there's some device control things, all this sort of junk down there. It's like, whoa, how was that important? Well, apparently in 1960 it was, but maybe we're not so excited about it now. But and then we get to some sort of ordinary characters start to get space, sort of things start to normalize out. We get some punctuation, then we get some digits, right? And then the alphabet actually was over on the right-hand side. I missed it as it went by. Let's do it again. Just so we, bang, bang. Oh, here's the deal. I'm going to do a lot of stuff where I just kind of get up on the command line and I'm just doing stuff, and I'm going to do stuff that maybe you haven't seen before, or you wonder, hey, that was a neat trick. If I don't stop and tell you about it, and you want to know what it is, just bug me. Stop, yell, hey, what was that? I want to know. Bang, bang is just repeat the last command. Right? You can also do bang a letter, like bang M, and it'll repeat the last command that started with M. And so there on the other side was where the A's were coming. So this is actually two columns. It's a little hard to see that, but the left side being the numbers 0 down, right, and then over there, 64 picking up on that side, so the second half of the ASCII set over there, and then we see all the letters in order and all blah, blah, blah. All right, so if I say man ISO, okay, there's your first clip. So man ISO, and I hit tab there for tab completion, and I'm having man tell me what man pages begin with ISO. Every one of these is a character set. A character set that describes how we're going to use those precious extra 128 characters in the upper side of the thing. They are all over the map, right? And if I read this one, this is considered the one, right? And you'll see even its man page, it says, which is widely implemented and may already be seen as the de facto standard ASCII replacement. Okay, I challenge that. Let's show you why I challenge that. I've got a file. Its name is Beyond ASCII. So let's look at where it is. So here, Go 7. Everybody should have an alias for Go 7 because there's no place better to be than the class directory. And so I have this code. It's sitting in CS107 sample lecture 4. So you can follow along. It's on your computer appearing now if you want to go take a look at it. And then there's Beyond ASCII. And if I cat Beyond ASCII, it has some ASCII characters. And then, according to cat, which is just the, dump the file, a bunch of things it doesn't know what to do with, right? So, okay, the de facto standard, at least cat's not in on this plan about the de facto standard. I say, well, Emacs will be in on the standard, right? Emacs, you can count on good old Emacs. Okay, notice how I typed E for Emacs. That's actually both lazy and bad typists. I cannot, E-M-A-C-S, no, it always comes out as like E-C-M-A-L, everything there. Okay, so E, because getting into Emacs is important. That Vim stuff he showed you, no. We don't do that. All right, so here's ASCII. Well, Emacs at least sort of took my numbers up, but actually printing them most helpfully in octal, because we haven't learned enough bases already, that we don't need to learn another one, base 8. But still not really helping me all that much, not pleasing me. Okay, well here, I'm going to go back over here. I got another plan. Let me get my, oops. That's too small to read, but don't worry. I'm just going to the same directory, so CS107 samples, and I'm going to actually open it now in Sublime. Okay, so here's Sublime showing me that it actually knows a few tricks, right? And so it actually managed to get my como está usted and my 3/4 minus 1/4 equals 1/2. So some of the things that sort of showed up there. But here I got another couple tricks up my sleeve, right? I'm going to show you that it just keeps going. Everywhere we go, we'll see something slightly different. Tilde CS107 samples lecture 4, and if I take this file and I open it in, well here, let's just open it in text edit. That's what will come up in, right? Hold it. No, it's not going to come up in text edit. Let's make it come up in text edit. Open with text edit. No, that wasn't it either. Sorry. We're having a bad day. I got to sit down so I can see what I'm doing. We made my font size even smaller than my old eyes can do, so I'm having to kind of look really close. Okay, I'm opening with text edit. Here it goes. And in text edit, yes, I'm done with you. Oh, look at that. Well, como está usted and my fractions, yeah, it's just all gone to total pot there, right? Like things that I was trying to say. So had I sent this to you and I thought I was respecting your language and showing you that I know where the proper accents go in your name and stuff like that, I would end up looking like a total idiot when you got this and everything had kind of turned into something else. However, you can see sort of funny things like this, which is apparently when you're a major computer manufacturer and you feel like taking one of the upper ASCII characters and just mapping it to your logo, you get to do that. And so there you go. So if you load that thing in a browser, like that's another way to kind of see it, yet another version of who's going to do it what. Let's have a good old Chrome open that for us. So this means if I put these characters in a web page and hoped that people would be able to see them, whoa, look at that, right? It's all Cyrillic. Apparently that is more Russian hacking. They've gotten into the Google team and have taken over the whole upper ASCII. All right, so de facto standard, nonsense. All right, that's the point of the story. Up there, all bets are off. What's happening up there? The real deal is Unicode, right? So we saw Unicode in the first assignment. If you have not gotten to that one, it's the very last problem on the problem set. And that actually is the well-designed, huge committee, lots of thoughtful people, lots of years, right? Getting it right for all world languages, right? From Navajo to Klingon, right? You know, it's kind of to Egyptian hieroglyphics and everything in between. So, but having to do so, it really requires a lot more space, right? You can't get by with an 8-bit character and cover, you know, millions of different glyphs. So there's actually this whole kind of architecture to it that allows for a variable length encoding and all these kind of wacky things to help make that work. So just so you know, what's going on with characters. All right. Have any questions about my little speech there? Okay. I am just getting rid of these things. Okay, go away, go away, go away, go away. There I am, good old Sublime Text. Gotta love Sublime Text, okay. Emacs, I was gonna show you in Vim, but here's the deal. If I get into Vim, I can't get out. So, so we just won't show it. I don't know what, Chris can show you what it looks like in Vim. Yeah.
So for the standards, any number above 127 in character doesn't mean anything?
Yeah, it just doesn't mean anything. You know, there are some things that they'll collide, you know, that they'll be the same on, some that they won't. And so there's all those, if you look at those ISO 885.9s, there's 20 of those, right? And so there is a mechanism, for example, for web pages and email where you can tag something and say which character set you're using. That's hugely important for interoperability once you're using those characters. So what I was doing there was I was kind of cheating a little bit. I was putting the file up with no, you know, metadata that said what kind of character set. If I just attached enough thing to say this is Latin, such and such, then it would we would be able to kind of, you know, your browser knows how to respect that too. So if I made the file to actually carry more information with it, we could still exchange. But just the raw bits, you know, it's a free for all what you're going to send and receive, right? Oh, let's say, so let's say we look at those 7 bits, right, and we count up the number of ones, right? And let's say that if it were even, if we have something we call even parity, we'll say, well, if it was already even, then we don't add 1 here. We're trying to make sure that the whole byte has an even parity when we're done. If it had 3 bits on and the other 7 bits, the other 4 bits are off, we would put a 1 in the upper bit. And that way we could always check by counting up the number of bits that were on in the 7, and then checking that parity bit, and if they coordinated such that we had an even parity, whatever our rule was, then we would know that, okay, it looks like that byte came through intact. If somebody managed to flip one of the bits, just in transmission, just a little blip and glitch or something like that, then we would be able to detect that because the parity would not match. It would be like, oh, this byte has, so it's like a really, really primitive, what we call kind of an error detection or correction information we could have there. We don't know which bit's wrong, right? We can't really do a lot with that, but it could give us just a little measure of detection of the integrity of the data. Okay. So let's just code a little bit of stuff with chars. So if so I've got my code here, and even though I love Emacs, I'm going to do it in Sublime because it's going to make it a little easier for us to follow along with what I'm going to do here. I'm going to make that just a little bit smaller so we can look at it all together. Okay. So I wrote this little function, characterize. It's the perfect function name, don't you think, right? You give it a character and it's going to tell you about it. It says, what are you? What kind of character are you, right? You know, and so at 8-bit, we get this little 8-bit value and we want to figure out what it is. And I'm using a bunch of functions that are from a C library called C-type. C-type for character type. And functions like is ASCII, is digit, is alpha, is punct. So here's a kind of a nomenclature we're going to get used to. So back in the 106s, you know, A and B, right, we had a very long and informative names to our functions and our variables, right? Your section leaders were often encouraging you to really make it very clear what this function does and stuff like that. C comes from a very different tradition in terms of naming conventions. And one of the extremely odd naming conventions you're going to run up against is from a very, very old limitation that back in the days of yore, function names were limited to 8 characters. Okay. 8. That's what you get. You get 8. It actually wasn't a limitation of the compiler, it was a limitation of the linker, but that's notwithstanding, right? And so as a result, any C function that you see on the standard library is going to have a name that's 8 characters or shorter, And they will do whatever it takes to get their idea compressed into 8 characters. Subtract some vowels, throw away any underbars, right? So is digit, is ASCII, is alpha. Okay, we are thrifty. Remember, thrifty, ball of twine, string. It's all there. We don't go that. So you'll get this feel when you start seeing these string marks. They're like, why did they name them these cryptic, stupid little things? What's STR doing, right? Like there is a much better name that they could have given it, and they did not. And you have to kind of look back 50 years to know how we got there.
Is there any reason they don't use camel case?
They could have as well, right? Like the C has always been a case-sensitive language, right? So in fact, right, it was an option. But I mean, even like back in the super old days, right, there were like even sort of questions about whether you had uppercase, right? Like that was, remember, you had to get extra expansion pack to be able to handle that. So a little bit just shows the kind of very primitive roots we're coming back at, right? So don't be surprised you see this and you think, man, my section leader or my TA would smack me so hard if I turned in, functions named this way. And we're just going to tolerate that and kind of go with it. We're going to try to use our naming convention, so in terms of case and convention will be to use all lowercase, to use underscores to separate words, right? And to try to give, a reasonably useful name to the thing, right? It doesn't have to be like a whole sentence worth of stuff, but trying to use verbs, for example, for functions, right? So what does the function do? Try to use descriptive names for the variables and things like that. So. But we are going to be interacting with the C code in the standard libraries that's, kind of from an older world and kind of makes it a little bit harder on us to see what it's doing. So is ASCII, is digit, is alpha, is func. Those operations, I'll show you the whole list of them over here. I go back over here and I say, yeah, like tell me about, is ASCII. I'm curious. Man is ASCII. So man is your friend. Man tells you about Unix commands. It tells you about C library functions. It's got a wealth of things in sort of a bunch of different collections. And this is, for example, a whole sequence of the is blah functions, is x digit, is graph, is lower, is blank. So they're all there, right? And they all, oddly enough, they all take an integer and return an integer. That seems kind of stupid. You're right, it is kind of stupid. That's also another bit of a historical accident. So it has to do with there's one more character that we want to fit in 256, and we use an EOF sometimes as a character sentinel, and we don't want to use one of our 256 patterns for that we already have in use for other things. So we kind of use the 257th pattern to be EOF, which as a result means we have to have a slightly bigger type to pass to these functions. So, and they're there, and they largely work by arithmetic on the character. So for example, like if I were to, well, let's just run the program for a little bit and then we'll come back. We'll talk about writing a little bit of this. So if I say make, and I've got, so the functions I have here are like, chars, client, a bunch of things. It's the chars function that I want. If I try to run it, it says, oh, you're supposed to give me some characters. And I was like, okay, I got some characters. I've got A to G. And it says, okay, A is ASCII 97, hex 61, and it is a lowercase letter. G is also a lowercase letter. If I say, oh yeah, well, how about 0 and plus? And it's like, okay, it's a digit with value 0, it's punctuation. Okay, how did I figure that out? Right, I just passed it by these is digit. And then here's actually where I'm counting on this fact that there is a rhyme and a reason to the ASCII set, right? Which is that if I take the character CH and I subtract the character 0 from it, be careful, that's the digit 0, right? That's not the number 0. I get a distance, it's like how far away in the ASCII set, right, is CH from 0. For the digit characters, which are in sequence in the ASCII, that tells me its numeric value. Okay, that's kind of neat. Right, I can write a for loop that iterates over them. So if I write the loop and it takes char start, char end, I can go for ch equals start, ch is less than or equal to end, ch plus plus. And so here I am just like treating characters as though they were numbers, because they are. Okay. And so I got myself a loop, and then if I go to here, whoops, I got an extra parentheses there, and I can say, yeah, why don't you show me the loop? Show me everything that goes in between first and second. And so they're integers, right? That means I can actually do all kinds of integer things on them. Some of those integer operations don't really make that much sense, right? Like I can multiply characters, I can divide characters, right? I mean, for the purpose of what I'm thinking of as character data, of course, those are not really sensible operations, but they might very well be if I'm treating them as like a raw byte and I'm trying to do just some operation on an 8-bit numeric value. But the fact that they're kind of freely interchangeable is sort of an indication that's of a little bit about C's philosophy about how it manages data. So in a language like Java, Python, or any number of sort of another set of more high-level languages, there's going to be a real notion of type safety and kind of boundaries between different types. That's going to say there's a character type, and it's really a character. It means it's a character. It's not just an interpretation of a number as a character. It's really a character, and so you can do things with the character that only respect its type. You can do things with integers that respect its type, and those operations may sometimes be the same, but may not in some other situations also. So it doesn't. So the language has a really strong notion of separating things and having kind of a defined domain for certain kinds of types. C is generally not like that. C is going to be say there's a machine structure, and it's basically it's an integer. We got a lot of integer hardware down here. It knows how to add and subtract and multiply, right? And it can do it on 1 byte things and 2 byte things and 8 byte things, right? That's great. It doesn't have all those things. How about we just use that for everything? It's like, okay, characters could just be numbers, pointers could just be numbers, right? Integers could just be numbers. Okay, I'm good to go, right? And it's like, yeah, that's it. I'm not building you anything else. I'm done. My work here is done. I gave you integers. It's the 7th day, and I'm resting. Actually, on the 7th day, they had to make floating point numbers, which aren't integers. But other than that, all the rest, right, is just integers. And so, oh, I've got this right. So other languages, sometimes you have a character you want it as a number, you actually have to go through a process to transform it, which sometimes is nothing more than just taking the number that's underneath it and giving it to you, but it doesn't let you be kind of fast and loose about what's what. So C lets you do what's what. It says it's a signed, it's an unsigned, it's a char, it's an it. You do what you want. I'll truncate, I'll promote, I'm totally good with you kind of having access to my raw bits and doing whatever you want with them. I'm not going to stand in your way. Sometimes you're going to wish it stood in your way, right? Like when you try to multiply 2 characters and you think I'm going to get, like you say, I'm going to take CH times 3 because then I want 3 characters in a row in a string and it doesn't do what you want, and you're going to be like, why did you let me do that, right? You did nothing useful to me, and you're going to be sad. But there are other days where you're going to be like, I'm glad that there's nothing between me and the metal. I can just do what I want. All right, we got some cares. Yeah, here.
You're assigning the elements of arguments.
Yeah. So I'm actually, I appreciate you asking this question, because sometimes I'm just going to throw some code in there, I'm going to sneak it past you, and you're going to be like, hey, wait a minute, don't you pull a fast one on me. The arguments that are coming in are strings, and that's what I'm going to talk about in a minute, right? And so I'm having to kind of jump ahead a little bit here. I wanted to get just the first character out of that string. So what's happening on first and second is I'm saying argv bracket 1, which is the argument to the program is argv sub 1, and then the dereference is pulling the first character out of that string. And similarly on the second one. So basically what I'm doing is whatever characters I type on string, like if I type the string apple and banana, it would just take A and B. And we're going to talk more about the star and the brackets all in a minute, so just kind of hang with me. But yeah, you're definitely right. I'm pulling a fast one there, but stuff in that code. Yeah, so the star is the dereference, right? And there's actually 2 dereferences in there. It's a little bit to puzzle out what's going on. One of them is the array that's picking off the nth string, and then the star, which is picking off the 0th char. But if you didn't understand that, don't stress just yet. We're going to get there. All right, anything else about characters you want to know? Okay, let's go back. I have another slide. Okay, I was going to make slides, but I suck at making slides. I just do. Chris is up here, he makes these pretty slides, and I feel really embarrassed because I have 0 aesthetic ability. I can write code, but I can't write in English or actually draw anything. So I tried to use his tablet. I took his tablet home this weekend, and I discovered that my handwriting is pretty bad in real life. It does not get any better when I'm doing it through some kind of, cold, weird plastic device. I thought I did not subject you to that. I'm going to try to learn by Monday. I'm going to I'm going to have a speed course in handwriting improvement this weekend, and by Monday I'm going to be better. All right, so things you can do that you can go, okay. All right, so there was my cares, that's it. See, that's what I do. That's the kind of slide I like. Let's go code. All right, now we got characters. Okay, they're 1 byte. We got some rules about the ASCII. We're feeling good about that. Now I need more than 1 character. I cannot get by on 1 character. If everybody had a 1 character name, that'd be fine, but that's not going to get us, all the words in the dictionary and whatnot. So we need to be able to kind of sequence them up. All right, well, we got options, right? So in general, right, there always is this idea that when you're building an abstraction, a language, a piece of software, an operating system, on top of kind of what the hardware does, like, the EE is handy this, amazing pile of silicon that does these strange, amazing things. But it's up to you to decide how you present that, right, to the programmer, to the user, right, who gets to interact with that. And what does it do? It's like, okay, well, we've got boxes that hold bytes, right? We've got this whole big array of memory that we have out there, right? And we want to have sequences of characters, right, as an abstraction that we can use. Well, we start with saying, well, I want to put together an aggregate. I want to have 4 characters, 8 characters, put them together. It's like, well, I have these types lying around. Remember C? It's like, hey, I gave you integers. Won't that do? You're like, well, I could take a 8-byte long, and I could stick 8 characters into it, like, A, P, P, L, E. And I have sort of 3 left over. I'm like, well, can I just leave them as zeros or somehow indicate I'm not using those? Well, Zelensky, that's bits, right? You notice your usernames on the student IDs, all 8 characters. Clearly somebody somewhere was like, hey, no more than 8, right? So if you could limit the world to 8 or less, like those old linkers, right? You could totally get away with just sort of jamming all your string data into a long, just passing around longs and being like, well, there's a string in there. You figure it out. But as soon as you need to store the Massachusetts Institute of Technology, into your database, you're gonna be like, uh-oh, yeah, MIT, come on, acronyms, it'll work. Stanford fits. Well, we're done. Who cares if anybody else doesn't fit, right? So we gotta get a little bit more. So if you think back to your 106 days, it's like, oh yeah, it's all about the array. It's all about the vector. It's all about the list. I know this. I got this, right? We've done tons of ways of managing, aggregate collections, index, blah 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 blah, right? So that's probably going to be the way we're going to go. But we're going to discover that C, right, isn't so big on fancy abstractions. It's not really so grand in its aspirations to support you in your needs. As I said, it gave you the integer, it gave you the character. Can you just make do, right? And it says, here, I'll give you, I got one more thing left for you. It looks in its back pocket and it says, I got a pointer. This is the key to the universe. That really is, if you summarize C down to something, it says, there is a machine, it is underneath you, and it has these raw bits, and I've given you access to those bits, and now I've given you access to the bytes by address. Go forth and multiply. Make it happen, right? This is all you're going to get, right? And then it turns its back on you, and it's up to you. All right, if we have the idea of an address says, there's a place in memory where you can go and access a character. Go to PO Box such and such, put your key in it, open it up, voila, there is that. And in fact, the sequencing is just going to be done by position and layout. I'm going to say, start at this PO Box, and then just go to the one right next to it, and the one right next to it. So taking an address, I start with some address. I say the address is 7, FFFFF0, right? And it says, okay, go there, and then look at 7 FFFFF1, and then 7 FFF2, and just every character you see is one more character in the sequence. So wherever I point to, so I'm going to talk about these things as pointers, right? That address is the address of a character in memory for which there's a sequence of characters. And then we need one last little trick, right, which is, how do we know where it stops? If I'm there with, at PO Box 22, and I look at 23, 24, how long is the string? Is it 5 characters? Is it 10 characters? Is it 200 characters? I need to know where the end is. There are options, like the whole system itself. It's like, well, what do? I already had to make some choices about what character mapped to what number. Well, I can make a decision here about what representation is going to enable me to do things with strings that's kind of convenient and whatnot. One representation that was chosen by Pascal, a language that none of you have ever heard of because it died off before you were born, but was still awesome, took the strategy of saying, let's take that first byte and we'll put the length in there. So we take the first byte, we treat it like an unsigned car, and we put a number from 0 for the empty string to 255 when we have that long string. And then after that byte in memory, we sequence out the bytes. So the string apple has 5 followed by A, P, 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 L, E. And then what we pass around is this address of where the length byte is, which then we know the characters follow in memory. And that version of the string is kind of handy, right? It means that as I pass it around, it's kind of a one-stop shopping. Like, I don't need to pass 2 things. I don't have to pass the string and the length separately. Like, that was another option I could have done. As I said, well, every string is 2 things. It's a pointer and a counter. And you have to always pass this little struct around to get there. But that's kind of messy. It kind of, complicates the interface. So trying to figure out how to jam the length and the string together into one thing that I can kind of uniquely identify as sort of a goal here. So if we did that, there is one really major downside to that system. What is its major downside? Yeah, you gotta find it. In fact, the string in Pascal was called the STR255, right? When you made it, it was like, it's right up in front. It was like, by the way, you know, if you have more than this to represent, you're out of luck. You're gonna have to string together, ooh, look at that, string together a bunch of these things to get to if you have a 1,000-character string. So if you were trying to do, let's say, one of those DNA sequencing and they have these million TAGC, somebody help me here. Yeah, GATC, something like that. You know, there's like, you know, millions of base pairs, you're not doing it for 55. All right, so C says, no, we're not into that. We don't like limits. We want flexibility. We want it to be as big as memory if you want it to be as big as memory. You want a string that's like a billion byte long, go for it. You've got a billion bytes in your address space, you can have them all. How else are we going to find the end? We're going to set them, right? We're going to pick a character, and the character that is chosen is the null character, that is 0. And so we say, if you see a bit pattern in one of those bytes that's all zeros, that was the end of the string. So good old Binky, B-I-N-K-Y, with its null byte. I'm going to write that null byte in the kind of precise way in C. We talk about the 0 character as open single quote, \0 close single quote. That backslash is important because without it, it's just the digit 0, which is an ASCII value in the ASCII character set. The backslash is what's called an escape sequence, and it's saying, no, I really, really want the 0 value character here. That is the way we mark the end of the string. Now, we don't usually see that backslash in a lot of our usage of things. We'll see like double quotes around Binky, but then you will need to know that when you see double quotes around Binky, there is a backslash there, because no string can survive without it. Without a terminating sentinel, it's just not really a C string. It's got to have a stop. Way in the back.
So no longer does your first pointer lead to the length of the string?
No. So that was so maybe I'm sorry to have confused you. Pascal is just this alternate way. That's one way we could have done it, but it turns out that left us sort of high and dry on unlimited length. So C says, no, we're going to go with unlimited. Okay, so C says, I want to put the null terminator. Yeah, that way you'll know when you're there. Okay, so one consequence of that is it turns out we had to sacrifice one of our precious, 256 characters and kind of, make the sentinel out of it. So we lost one more character we could have put in our set, right? That's one minor, detail we lost with the C strategy. What is the other big downside of the C strategy?
I mean, because it's an array, you index to where the 0 character is and change it.
You absolutely could. That would be definitely bad news. You would be able to, though, and you would be able, for example, if you wanted to change that string or add something on the end of it, you would do exactly that. That actually turned out to be not so much a disadvantage, it could be an advantage. Like if I want to append to the string and I just go to where the null is and I start writing, I have extended this. That's pretty cool. I better make sure there's space there, though. That's, I gotta watch what I'm doing.
You can't ask how long the string is because it doesn't know.
Yeah, okay, so but let's say I'm starting with the string, I said, hey, how many characters do you have, right? Because I'm planning on copying you or putting you on the screen and I want to center you. It's like, does the string know? Like at least the Pascal string, it was right up front. I could just grab it right off, okay, I know how big it is. How do I know how long a C string is? You count. You count. You start at the beginning, you say, are you a 0? No. How about you? No. How about you? And I'm taking a pointer and address here, moving it up one by one by one. Eventually, 1,000 base pairs later, I get to the end of the string and I say, oh, there were 1,000. What about the next time I do the string length? What do I do? Oh, I do it again. Do I write it down somewhere? No. No, I didn't write it down anywhere. I just there's a function called strlen. It's in the string library. It's like, and you pass it this address in memory and it says, and basically what strlen does is it just counts in memory all the way until it gets to the first null byte. That's all it does. It's not smart. It's not an abstraction. It's not like having a communication with the string. Tell me how long you'd like to be, right? How long you think you are, how much, how long you aspire to be. No, it says, I'm just walking memory byte by byte by byte by byte. I get to a null byte. That must be the length of the string. So if I, for example, were to write to that I and put a null byte on it, and here's where if I were smart, I would have things set up. I'd write a 0 on top of the B or an I. It'd be really awesome. Just imagine it. And that would be, I have now truncated Binky into B. Right? I could just do that. And it's like, that's how I change the length of the string in C. Right? Is I just write a null byte somewhere else in the string, and it's like, now it's shorter. That's pretty wacky. Right? So we should start to get the idea that, in C++, in Java, in Python, in every well-meaning and supportive and loving language that you have spent time with, right? The language is trying to kind of give you a real abstraction. There is a string class, and if, for example, you take a string and you add another string to it, it concatenates them, or, and it knows its length and it's keeping track of it. It doesn't let you just kind of go in and kind of muck with things. C is not your well-meaning friend. C says, hey, I gave you the bytes, I gave you the access to them. What you do with them is your own business. Should you want to put nulls in the middle of it? Should you want to write past the end? Should you want to put a string together and forget to put a null on it? Okay, go for that. We're going to find out what happens when you do that. It's that the C language isn't really going to be able to stop you from doing those things. It's going to say, it's up to you. If you, write down the characters P-I-A-K-Y and don't put a null on it, and then you pass that string, you pass the address, let's say, where B lives to Sterlen, you might get the number 5 back. There's a chance, right? What was in memory there might be a 0. It might be 5 after all. It might not. It might give you the number 272. It might give you the number 1,445,000, right? Because, who knows? It's very unlikely to get that far before a 0 byte kind of just shows up in sort of random, informational entry way. But C is really not stopping you. It doesn't really have a real kind of boundary around the type that's very secure. This is part. I love C. So don't get me wrong. I shouldn't knock C. I love C. C is my mother tongue. I came out the womb. We were born together, in fact. That's why. And yet, understanding what it's going to do for you and what it's not going to do for you is the really primary sort of way to really bring it into submission for you. So realizing it's not actually out there to try to provide you a very clean and tight and secure, type-safe system. It's actually just giving you kind of this raw facility for how we manage bits and bytes and addresses, and then from there you can kind of imagine that you have this string thing happening on top of it, but it's all a little bit smoke and mirrors in terms of what the language will do.
You said that if you wanted to overwrite the 0 character
Yeah.
and keep talking, you would have to be careful to know that memory is available.
Yeah.
Imagine, without making the question too complicated, imagine that it has a list of pointers which are the list of memories that is allocated, but it doesn't know the end of them. So how does it assign more? How could you check whether?
Dude, you know what you're asking is, how do I write a heap allocator? I've got the answer to that. You sit in this chair for another 8 weeks, right, and then you'll write one. That's a great question, and you're totally looking ahead. It turns out it's going to require actually somebody keeping track. And I'll tell you this, C is not going to do it. So if you want it done, you're going to do it, right? It's like nobody's going to do this but you. So if you want to know how long something is, if you know how much you allocated, right? You can say, I allocated for writing and I put the null there, so Sterling will tell me. That's going to work for certain kinds of situations, but if you fail to follow your own rules and you start putting nulls in the middle, right, you will have the wrong idea of how much memory you have there, right? If you go past the null, you'll kind of overwrite things. And the idea of the boundaries between addresses, right? In your mind, there's this, it's sort of like you think, well, there's my dorm room, and there's my neighbor's dorm room, and I can't just push my bed into their room. And it turns out the walls in C, there are no walls, right? You push your bed into their room, and they're like, hey, get out of my room, right? No, it's like, okay, you just come back and somebody's dirty gym socks are on your bed, and you're like, awesome, right? This is the C world, right? It's not all that safe. Okay, so let's go write some C code. So I said we're going to pretend, right, that it's that we don't really know how strings work, and we just do stuff with them to kind of just learn a little bit about how they work. We're going to pretend that we believe in the string abstraction. There's a string fairy that's going to give us strings, and then we're going to manipulate them, and we're going to kind of learn what we can do with them as a client. So I'm going to start with that sort of idea, there's a string fairy, and I'm a little bit naive about strings, and I have the string fairy to help me out. So here's I have a little bit of code to just get us started. It just does some things with this car star. So the C notation for this, right, hopefully you saw this in C++, but I assume you're not super familiar with it. So kind of, don't be surprised when I try to be slow about it. Car star pointer is saying that PTR is a pointer variable, and a pointer is so I'm going to be very precise with these terms. Pointer and address, they're kind of the same thing, but they're not exactly. Address is a value. An address is a number that refers to a memory location. The way an integer value, 10, 20, that is an integer value, right? So an address is the address 22, 1,000,000, 1,445,000, right? we have a pointer variable, which is like the equivalent of an int, right? It can hold a value. You say int x, and you say x could be 22, it could be 45, it could be 110, right? So those integer values are stored in an integer variable. Pointer variables hold addresses, right? So the address is the value, the pointer is the data type that holds that kind of address. And pointer variables are distinguished by the pointee. That is a word I completely made up, okay? If you say that in some company, people will just look at you like you're a total, alien from another planet, but that's okay. We're gonna just go with that terminology. The pointee is the thing on the other end of the pointer, right? If I'm a car star, I point to a character. The character is the pointee, right? So an int pointer, a car pointer, short pointer, long pointer, all these things, that all the addresses, right, are all the same size, right? There is this idea of we're in a 64-bit address space, so we actually have 8-byte pointers. That's a really big space for numbers. So all addresses kind of really look the same to the machine, but by distinguishing what's at the other end of it, the pointee, it gives us a little bit of management over keeping it straight. What is at the other end of that pointer? Because if I just take an address and I say, what's an address 1,000? No one knows. If I just look in memory, I put on my X-ray glasses and I go look at the byte 1,000 in memory, all I see at the byte 1,000 is 8 zeros and ones. Was that a character? Is that the first byte of a 4-byte integer? Is it the middle byte of a 4-byte integer? Is it just garbage because nobody wrote anything there? No one knows. The only one who knows was you. If you take this address and you put, the address in the pointer variable, you're supposed to know that what I am storing there is an int, is a car, is an array of this size. So if you haven't done your work to keep track of what it is, just knowing that pointee type is really not going to save you. It gives you a little bit of tagging in the program that says I know what's at the other end of this, but not any real, in reality, there's no guarantees about what it actually was put there because that's up to you. So we'll kind of have to go with this. So I have a car star. It's an address. That's a location in memory. And then the first thing I did was I just print the address itself. So %p is the printf directive that will print the address as a number. So I can see what kind of numbers are addresses. We're going to see that. And then it does an flush, which that's just a little bit of magic. I just did that for, there's a reason that it's going to be, don't ignore that man behind the curtain. All right, next 2 lines. Printf says, and now let me show you what's the pointee. And here I'm using the dereference operator on the pointer, which also happens to be the star, which was also used in the type declaration to say it's a pointer. Could we not overload the frickin' asterisk so much, right? It has 2 very they're related but not exactly the same things. One of them's talking about the type system. I'm a pointer to this. One of them's talking about dereferencing this thing. And then there's yet another one, multiplying. Just when we thought we were safe. But so this use of the star here is saying, reach out to that pointer, that address, go get the 8-byte thing, the 8-bit thing that's at the other end, and then the %c says, interpret it as an ASCII character. Show me it's an A or a plus or whatever it is. And then I said, that address, show me %s of it. And the %s is the string directive for the printf that says, go to that address and read characters and print them out until you get to the null. Okay, so we should see an address that wants to be printed in hex. We should see the first character, and then we should see the first character followed by all the other characters when we try to show a pointer, show string in this case. Okay, kind of neat. And then I'm going to start with that one, and then we'll go down and we'll look at the operations in a minute. But I'm going to actually say, okay, well, let me just run this program. And in fact, the way it works is down here at the main, it just asks me to give an argument in argv, and it's going to use that string. So whatever string I type on the command line, I check, binky, then it's going to show the binky pointer. Show me where it lives, show me the first character, show me its contents. All right. We'll see what it does with it in a minute, but we'll just start with that. Okay, so here I am. This is in lecture 4, and I say, I would like to see about binky. Okay. Pointer holds the address. Oh, my lord. Look at that thing. 0x7FFFD07733CBB. Okay. It's big, right? So strings are somehow being put somewhere kind of far away. They're not at address 100. They're not at address 1,000, right? They're not anywhere near any number that I know the number for, right? It's like a gazillion, way up there. Okay, that's a location in memory, like anything in C. I just wrote down an 8-byte address there. The character at that address, so dereferencing once, pulled the B, and then when I told it to print as a string, it said B-I-N-K-Y. No, okay, stop. So printf just walked through the string until it got to the null, and stopped for us. Okay, cool. I got a string. All right, let's do some other stuff with strings. Okay, so I have a couple little things I'm doing here, and some of these are good things and some of these are bad things. So my intention is to say, well, what happens when I do stuff right? What happens when I do stuff wrong? If I tried to print the string hello %s, that should work just like the one I saw a minute ago. I should get to see Binky from that, right? And then I said, take the strlen of that thing, right? So I pass it to the strlen function, which is one of the C library functions in string.h. There's a whole set of these functions. Here, I'll actually show you what they are. If I go back over here and I say, man string, tell me everything about strings, and it says, hey, I got your stp copy, your stir case copy, stir cat, your stir car, stir comp, stir col, stir copy. Okay, keep going. There are a few that are more than 8 characters. Woohoo! Welcome to the new millennium, right? Those are actually non-standard. Stir case comp and stir end case comp were actually added. Like, I don't know, 20 years later, we thought, hey, wouldn't it be nice to be able to compare case insensitively? And since we've got extra characters now, why don't we use them? The earlier one was actually I stir comp, so it just fit in 7. But so yeah, stir, 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 step, stir, toke. I'm telling you, you got them all. It's like a whole new language. And then this one tells you, okay, what the prototypes are for each, and then down here, there's, it says, the string function performs string operations, see the individual man pages. So basically all this tells you is like, okay, I learned a bunch of names, and I have to go look up those names. Basically what it gave you was a bunch of pointers. That's what it gave you, right? Here's a pointer, go follow this and see what you get at the other end, right? So this is a man page that points to other man pages. So if I really want to say, yeah, what does strlen do? I can say, oh, man strlen. And it's like, calculate the length of the string. It calculates the length of the string, excluding the terminating null byte. We know that calculate sort of sounds like too smart, too robust. Really, it would be more, if it said more fairly, it said, I'm going to walk through memory starting at this address until I find a null byte, and then I'm going to tell you how far I walked before I got tired. That would be more accurate to what it's actually doing. This sort of, I can figure out the length of the string sounds like it's omniscient, but in fact, it's just dumb code. Question?
Can you repeat the difference between like stir comp and stir case comp?
Oh, so one of them is case insensitive.
Okay.
So stir comp is A does not match, capital A does not match lowercase a. Stir case comp says they're the same.
And it, like you said, it was standard or not standard?
It's not standard. So case comp was added. So the ANSI standard was sort of locked down in like 1990 or something like that, right? And then there was a kind of, they keep revisiting it and sort of improving it, but most of what kind of it does was really sort of just, fossilized, let's say, in 1990. So you will find that the kind of modern things you were hoping for really did not, C has not been really moved forward with those things. It tends to be like kind of, it's a classic, right? It's a classic. C++ is where they jammed all the stuff everybody wanted year after year, so it just keeps growing. But C, they kind of keep small. Question? So, say that again? Because I used %s, right? And so what this is I'm counting on printf to be my buddy here, right? I'm not doing any hard work, right? I'm just passing it off to somebody else, right? So I said, so when you give the directive to printf, you're saying, do this with my argument. So %p says, I'm giving you a pointer argument, would you just go print the address as a hex? If I say %s, I'm saying, oh, what I gave you is a string, and string in C speak is, I gave you a place in memory where you can just start pulling bytes and treat them like characters until you get to a null. So that's just the printf specification says %s says this, %d thinks it's going to get an integer, %c thinks it's going to get a character. So it's just, I'm getting printf to do my dirty work for me. I could print it myself. So if I didn't have a printf that did this, right, I could do a print the first character, add 1, the second character, add 1, and keep going until I got to the null. And that would also work. It would just be, I'm counting on somebody to help me out here.
What's the %LU?
The %u is for a long unsigned, right? So
That's what string length returns.
So string length returns a size t, and so size t is in our system is effectively a synonym for unsigned long, and that's due to size t has to be able to hold the largest size of anything we could have in our system. In a 64-byte address space, we could technically have something as big as 2 to the 64. That's never going to happen, but we've got a size t waiting to hold on to it if we do.
Yeah, so what happens if you run that print statement with the pointer you pass it and actually start the string?
Yeah, let's do that. Let's find out. That's a great answer. Let's do it with well, here, let's just do this. Let's say I say show string copy. Okay, this is fun, right? Copy, car copy sitting right there. What's the value of copy right now? Right, if I have an integer, if I say int, num, and I don't say what it is, what value does it have? We have this in parity, if you remember back to lab. It's like, is it 0? It's a garbage value, yeah. It might be 0. There's a 1 in 4 billion chance it's 0. It's probably actually higher than that, really, in terms of random entropiness. But it might be 0. It might not. Let's find out. Okay, so I said, show me the string s, then show me the string copy. Let's just find out. Okay. The warnings I'm going to come back to in a second here. I say, okay, let's run that program. Oh, it wants an argument. I say client Binky. Okay. Pointer holds address this, char address, B. Okay. Pointer holds address 408, 85D. The character of that address is H, and then next to it is some, maybe upper ASCII, and then another H, and then a 9, and then some more upper ASCII, and then a U, whatever, crap. Yeah. Eventually, it got to a null, though, right? It looks like about maybe 20 characters in, right? So there you go. There, I have just pulled the curtain off. What is a string? It's like, I don't know. A string is what you make of it, right? If you go to this place in memory and you say, there'll be a string there. That's what I told Sterling. I said, here's my string. Go right there. Count characters. If I took the Sterling out of that thing, it'll come back as 20, right? Whatever it is. It's like, well, that was the first place I found a null, starting from where you told me to look. And then printf said, okay, well, I'm just taking the bytes and mapping them onto my little ASCII. I'm glad I could be of service, right? No one here noticed that this was just a total nonsense thing to have wanted to do, right? That's the beauty of the string. It's an abstraction that's not really an abstraction, right? It is, offering you very, very, very little in terms of sort of full-featured concierge service, right, with regards to strings. It is just an address, and you're like, okay, I got an address. Like, I could do stuff like this. Okay, this is gross, but just go with me, because it'll be fun. If I say int num equals, and I say 107. Oh, no, I need a bigger number than that. Negative 107. Okay, and then I say, instead of asking it to do this, I ask it to do the address of num. Okay, so num is a 4-byte variable, right? It's sitting on the stack. It's got 4 bytes of, 2's complement sort of numbers in there. And I said, yeah, just take the address of that thing, right, that's sitting there on the stack and pass that to showstring and tell me what it looks like as a string. Okay, the compiler's going to yell at me about this, but it's going to let me do it because I know the magic word. And it says, warning, passing argument 1 of incompatible pointer type, expected car star, but the argument is type int star, but it's good enough to go because it turns out int star, car star, whatever. Come on, we're all friends here, right? It was an address. Let's see what it prints. I have not done this. This is like, not staged. Let's find out. Hey, look at that. That address is sort of interesting that it's actually kind of close to the one that the argv came out of, right? And it's like, yeah, it's got some 4 garbagey characters, and then it hits sort of a @ sign. Okay, again, it didn't know, right, that those bits were really the number, 107. The reason I didn't put 107 positive was because I was thinking, okay, well, there's going to be these. 107 has a bunch of 0 bytes in it because it's a very small number, right? So a 4-byte number has only bits on and the low byte and the little ending. It's going to make a really short string, so that's why I flipped it around so I would end up with a bunch of 1s in the upper bit, so I had something more interesting to look at in terms of my numbers. So, but yeah, I got some junk out of it. But again, nobody knows, right? It's all between you and the machine. What's your data? They're bits, they're bytes, right? Like, is it a car? Is it an int? Is it a float? Well, it's what you make of it, right? And C is going to be really very permissive about letting you dictate what you think it is or what you want to do with it. It's not going to hold you back from, accessing your data in any way you want to. All right, so let's look at a little bit more of the things I'm doing here with this. So I'm going to take that out because let's do this. All right, let's get you some real garbage here because you really need to enjoy. There's a certain experience in C that you have to have before you can call yourself worthy, okay? And the expression is going to go like this. Okay, I just set copy to be the number 1. That seems like a bad idea, but let's see what the compiler thinks about that. Oh, it makes a pointer from an integer without a cast. Okay, but if that's what you really wanted, I'm good to go. So it said the address you're looking at is post office box number 1. What's going to be in post office box number 1? Let's find out. Okay, here we go. Ooh, look at that. That's what happens when you get a segmentation fault. There we go, segmentation fault for dumps. Anybody ever seen this thing before? Ever had the opportunity to experience a seg fault? You all are going to get this opportunity, okay? You're going to take this and frame this, right, and put it up on your walls like the first dollar you earned, right? There's going to be the first seg fault you have earned, right? And you're going to print it, and I'll sign it for you. It'll be worth something someday because I'm going to be very, very famous, right? And you say, yeah, that was it. What is a seg fault? Well, I made a slide for this because I thought it was actually a little bit of there was some language I wanted to share with you about it. There's my code, right? Because you're going to see this a lot, and I want you to have an understanding of what does it mean when your program runs into a seg fault. What is it trying to tell you? How does this relate to what is happening kind of underneath at the meta, right? C is largely just passing through kind of its own experience interacting with the hardware here. So you have this idea of an address space. Your address, when your program starts, you have this address space that actually kind of is unique to your program. It starts at 0 and it goes to 4 billion. And it's kind of your own. It turns out there's a lot of programs all running on a system at the same time who all believe they have their own address space and it's distinct from everybody else's. In fact, there's a really neat sleight of hand that the operating system is providing to make that really work safely. So your mail program and your browser, right, and your SSH terminal, right, they're all running kind of and kind of sharing. There's one physical set of chips, right, that are actually where your RAM is and stuff like that. But there's a lot of game playing where everybody feels like they have their own kind of full thing and whatever, and they're accessing it. Okay, so you get to know I can talk to address 0, I can talk to address 4 billion, right? I can put that number into my program and say, go to byte 0, tell me what's there, tell me what's at byte 1000. That's not a very normal thing to do, to just pick an address out of the hat like I did there, but it is possible, right? Because it's just a number. I can pick a number and then say go to that place. The truth, though, of course, is there's not going to be 4 billion bytes of live memory. That we're going to be using a tiny, tiny fraction of that in our program. And so to keep track of what we're using and not using, there's going to be this notion of a segment. And the compiler and the operating system sort of together are kind of coordinating on what segments does this program need and arranging them in memory and then kind of leaving everything that's outside of those segments what we call unmapped. So there's going to be a section of memory that's going to have where your code is, where the actually compiled version of the instructions that are being executed lives. That's called your code segment. Sometimes it's also called the text segment. Even though text sounds like it would be English, it's actually not. It's code. There's a data segment where we're storing variables, and the global variables and string constants go there. There's going to be a stack segment where we're keeping our local variables and parameters and things like that are going. There's going to be a heap segment, right, which is where the dynamic memory is coming and going from. If each of those is, let's say, a couple tens of thousands of bytes, maybe 100,000 bytes in kind of an ordinary program, right? That's just this, 1% of 1% of 1% of this, 16 exabyte region that we have. Everything that's outside of that is what's called, is unmapped and inaccessible. If we try to read or write any address that's in that big gray zone, right, it will create a segmentation fault. And what actually happened there was it went to go to that address and either read or write it, right? The hardware went to say, okay, where did I put those addresses again? Because I don't have them kind of resident right now because I'm busy with this other stuff, but now it's time to go get them. And then it goes to get them and it says, wait a minute, right? It's like you're checking into the hotel and you say, oh, my reservation is for room, 1,455. You're like, well, we have 300 rooms, right? And so do you just go up and throw them off the roof? You're like, no, you stop at the front desk and you say, I'm sorry, there is no key to that room. That doesn't exist, we manage care. So the idea is that there is a coordination here between the operating system and kind of that has what's called protection layer that says you can't get to that memory, and then you get a segmentation fault. You also can get segmentation faults from slightly more ordinary things. So the case I had there was I just picked an address at random. So if I were using an uninitialized value, it could be a completely wild pointer. The odds that if you just took any number at random, that it would be valid and in one of this tiny fraction of in-use addresses, is very, very low. So pretty much a wild pointer is likely to create a seg fault when you try to access it. There's also the case where This is a much more rare case would be if you're right at the edge of the segment, so somebody's got to be last, right? So maybe the last variable that got allocated in the heap is sort of is right at the edge, and beyond that is actually not in use right now. That if you were to cross over just past the end of your thing, you might fall off the edge of the segment. Very, very rare. Again, you have to be kind of that one fence post case, right? And another case that comes up is there's some segments that are marked read-only. One key segment that's marked read-only is your string constants. So when you put a string in double quotes and you say hello, right? Well, somewhere in memory there really is the sequence HELLO null byte. And the compiler kind of set all the string constants together in one part of the data segment, and it marked it read-only. So if you try to write to a string constant, try to change one of the characters, right, you'll actually get a seg fault. And so those all get reported the same way. The wild pointer, the past the edge of the segment pointer, or the writing to a read-only segment, they all show up with the same thing. The message is just segmentation fault, core dumped. You do not have to say you're sorry. Like you never have to say you're sorry. It's like segmentation fault, and that's all you get. So we'll call that a crash. We will experience this a few times during the quarter. Our programs will crash, right? And it all comes down to the things that really make programs fail, right, in these catastrophic and spectacular ways are accessing bad addresses. You don't get segmentation faults from integers, right? When they overflow or they underflow or they, things happen with them, you use an uninitialized integer, right? You just get a junk value. If you're counting something up and you can start by initializing your sum to 0, well, then you get garbage out of it, but you don't crash, right? You get nonsense, right? The program prints crazy things, whatever. You flip around, you lose all your money, like whatever, but that you don't crash, right? So crashes are really kind of unique. There's a particular sort of set of events that have to come together. It's that I have this address, and either the way I calculated it, or where I got it from, or how I initialized it, or kind of, what my interpretation of something is, actually has caused me to get outside the segment, and then I get this hard exit, right, with no information, no real clue. And so if I go back to that program and I actually try to see what I'm doing, this is a good time to say, hey, what if I GDB that thing? And at least here, right, then I get to find out where I was, right? So I can say, oh, I'm right at this line, I'm trying to print this thing, and then PTR's value is hex 1, and then it actually has in this angle brackets there, error cannot access memory address 0. So I'm getting a little bit more information, whereas what I saw at the shell was really just the barest of goodbyes, right? As the program was leaving, I'm actually here, I'm in GDB, and I'm getting kind of all this, okay, I get to see where am I can do a backtrace, right? I can't type the word backtrace because here I'm just BT, that's what I do, right? I'm all about the shortcuts, right? And so, okay, I'm in here, I got this, so it kind of tells me where I'm at. I can look at my variables, I can print the value of PTR, I get all this insight that I can't get if I'm not running in the debugger. So the debugger is my friend. All right, question?
The memory that's outside the segment, what is being done?
So it mostly just doesn't exist, right? It's like the operating system is sort of written down. You're using here and here for the stack, and you're using here and here for the heap, and you're using here and here for this. And so when you give it an address, it kind of looks it up and it looks into this table and says, okay, where's that address? Oh, I don't have anything in that address, and it just blows you off. So there's really almost nothing there. It's like you can imagine it's like a sparse sort of array where it's written down what is in use and everything else is not in use. And if you're not in the in-use list, then you're bad.
You got a seg fault from an infinite loop. Can I run out of space in my segment?
So again, that would be if you're running off the end of the segment, so like a stack is a good example of the stack segment. They have some fixed size to it, and if you got really deep in the recursion or you built some really big variables, right, you could essentially exhaust that, and that would be that case I said where you went off the end of that segment and you crossed into the no man's land where you were supposed to stop. And so you can absolutely get a seg fault from recursion that goes too deep or has just extremely large stack variables, right, larger than the stack capacity. Oh, they absolutely are consecutive. That's the only way anything works in C, right? Is that 0, 1, 2, 3, 4, right? So, this is one long linear sequence, right? And all of the math that we can do in terms of moving forward and back, sort of up and down, numerically, absolutely talks about contiguous regions, right? So, when I talk about an integer, there's 4 contiguous bytes there. It's starting at some address, and address plus 1 plus 2 plus 3, right? That is the group of 4 bytes that represent that integer. It will never be anything other than that. It will always be this. Everything hinges off that working bit. The numbers, the address is treated as numbers, right? Indexed, right? The way you might think of an array.
Do programs get any control over the size of the segments that they get?
They do actually. You can negotiate with the OS. You can actually bring online those segments. We won't see that, right? That's kind of beyond the scope of where we're going to be. So, but yeah, there are ways you can actually monitor it yourself and kind of find out stuff, and you have to just interact a little bit more with the raw system and figure that out. Mostly, we're going to see it as something that's kind of provided to us, right? It's our job to stay in the boundaries. Sure.
Catch in the segment that you call?
You can. So there's a whole OS layer called stuff called signals, which you can go Google, right? About how do I catch a signal? What do I do about it? In general, though, once you have a bad access, pretty much things have gone pretty far astray. So mostly, what you really do want to do is shut the program down. But for a program, for example, like that was maybe some long-running server that was doing some experiment, you might actually want to catch it and sort of somehow figure out how to restart and kind of get things back on track. But all right. So let me go back and look. I have some broken code in there. I don't want to leave you with this broken code, so because I want to show you some of the things that I can do with pointers and with strings being pointers, right? That is allowable but not very sensible. So as I said, we're kind of leveraging this idea of this integer type that Chris kind of got us all through, right? Well, pointers just being integer types means that integer operations largely apply to pointers too. So I can say pointer plus 1. I can say pointer minus 1, and that actually takes the address and goes up or down 1, right? For these car star pointers, right, it says, oh, I'm pointing to this character in memory. If I advanced by 1 or I retreated by 1, I would be talking about the character 1 byte to the left or the right, in terms of if I think of it as a horizontal row. I can also do things like look at them as numeric in terms of comparison. So if I said if S equals Binky being the string constant there, what I'm actually saying here is I'm not really comparing S to Binky, right? So let's actually run it and see. So I said, if S is equal to Binky, if S is greater than Binky, right? Tell me, is it equal? Is it? I want to see if either of those fire, right? So if I make the program, is my code broken right now? I can't even remember whether I've broken it so badly. Yeah, it's definitely broken right now. Let's take that out. Let's have our code actually work. How about that? Okay. And I say, yeah, well, if I let's put Winky in first, because we know Winky shouldn't be there. And it says, okay, it didn't fire on it is equal to Binky, but it says, yeah, it's greater than Binky. Oh, well, that's good, because Winky should be greater than Binky. Well, that sounds good, right? Okay, well, if I said, it's Ant, and you're like, huh, well, yes, actually, Ant is also greater than Binky. Okay, so there's not what form of alphabetization is this actually using? Well, how about I just do it? I'm like, oh, come on, it's Binky. Binky is Binky, right? No, Binky is not Binky, right? Okay, let's go see what we got there. So what this is doing, right, this equals, and then the whole host of less than, greater than, and all those kind of things, those operations are defined on pointers to mean take the addresses and literally compare the numbers. Are they pointing to the same place in memory? Is it the address of this one less than the address of that one? Okay, those are odd things to want to do, right? Because is it really that useful to know that some address is lower in memory or higher in memory than another? But that's how they are defined. They operate on the numeric interpretation. So an address being an unsigned long in this world, right? Like, oh, it's a number, and you can tell me whether that number is bigger or smaller than this number, or whether it's equal to it. So although those operations are defined right on those pointers, they don't have a lot of sensible meaning, right, in terms of doing sort of more interesting things. Like I probably want to say, do they point to the same sequence of characters, right? And in which case, in order to say, is this string the same as that string, then I can't do it with just a single operation, right? If it's 1,000 characters, I got to look at 1,000 characters to figure out whether they ever differ, right? So I'm going to actually do some work. It's going to take a loop. And although I could write that loop myself, I can also leverage my string library functions. There is a strcomp in there, and I could say, yes, if strcomp of S and Binky, and the behavior of strcomp is such that it returns a 0 when they, sorry about that, I got my prints in the wrong place, when they match, or it returns a negative number if the first operand is alphabetically or lexicographically precedes it, and vice versa. And similar here, if I said strcomp of, and I will do this one, I'll let you go, so I know I can feel with Russian, I'm sorry, then I can see the real truth about this. If I say client of Binky now, it says, yes, it is Binky, and if I say client of Winky, it should be it's greater, and client of Ant, and it should not be. All right, we've got more to go on Monday. I will see you then. Thank you for coming.